Okay, so I want to pick up. I want to pick up where we left off last time by saying that computers define and are defined by layers of abstraction. Okay, we can't talk about what a computer is without talking about the layers of abstraction that we're working at and the layers of abstraction that are defined for us. Okay, and you recall this is a week ago now. But hopefully you'll recall that we were talking all the way from the ground up, from bits all the way up to files and all the way up to, in fact, we stopped, historically speaking, at multi-programming, running multiple programs at once. At each level, it's possible to talk about what a computer is in a different method, in a different way, okay? And at each higher level, you are taking for granted something below in the lower levels, okay? And that's what a layer of abstraction provides for us. So now we want to kind of really shift into the topic of the semester, which is what is an operating system? Okay. Now let's ask a similar but importantly different question. What does an operating system do? Okay. And what an operating system does is it provides layers of abstraction that are convenient for the user. Okay? How it does that depends on which layer of abstraction you're talking about. Okay? And that's why there are, when we talk about, and you've seen this in your reading, which hopefully you've been keeping up with, and if you have, no doubt you've seen this, that's why there are competing metaphors when you're describing what an operating system is, okay? Because you can talk about what an operating system does in at least two fundamentally different ways. Now, those fundamentally different ways are linked together because they are consistent across all operating systems, but they are different viewpoints of what we mean when we're talking about an operating system, okay? So like, even on day one of an operating systems class, there's not a cut and dry definition for what an operating system even is, okay? There are discussions to be had about what becomes what part of an operating system. Should this be included in an operating system? Should this system functionality be included in an operating system, or should that be an application, right? There's no hard drawn line between the functionality provided by the operating system and the functionality provided by an application. And you can move applications into the operating system. You can move parts of the operating system out to applications, right? Depending on the design that you want to have for your particular computer system, okay? So we're not going to talk about a perfect operating system. We're not even going to choose one operating system to talk about. There's no operating system design that's handed down from on high, came down from Mount Olympus, and was given to Alan Turing and John von Neumann back in the 1950s, and we've all been using that operating system since. No, that's simply not the case. Operating systems have evolved, and they continue to evolve. Okay, and we're going to talk some more in today's lecture about why that is and how that is. But what you need to take from that is that what we're talking about in this class are fundamental principles that all operating systems today have to wrestle with, okay? And not just fundamental principles, but really the abstraction layers that those principles drive, okay? And again, I'm gonna get into more detail about what that is. But if you look at the chapters in the Xi book, you can kind of see where those fundamental principles are broken out. Each one kind of gets its own chapter, okay? Right? So what are the competing metaphors, right? Metaphor 1 and metaphor 2. Well, the first of the two most often used metaphors is that the operating system is a resource manager. Okay. Now, you'll recall, so I'm going to drill down on what we mean by resource manager. You'll recall in our odyssey through the evolution of computers from last week, that where we stopped was back in the day, early computers ran only one program. Then they unloaded the instructions and the memory for that program, and then they ran the next program. Okay, does that make sense? How many programs can your computer, your modern computer, run at once? Okay, there is no good answer to that question. Because if you say, my modern computer can run hundreds, if not thousands, of programs at once, from a certain point of view, you are correct, right? Let's see if we can pull up the task manager and look at all of the processes that are currently running on just this machine that I'm sitting at. It takes me a good few seconds to scroll down through all of them, okay? Most of them are completely idle. You can see some of them are jumping in, jumping out. As I move the mouse around and hover over stuff, some of them are taking up some CPU cycles, and then they go quiet, okay? If you said all of these were running simultaneously, you'd be correct from the user's viewpoint, okay? Now, if we go down one layer of abstraction, though, into the operating system's viewpoint, how many of these programs can be actively being processed at a time? Just one, right? So we want the appearance. In fact, we have attained the appearance of multi-programming. Okay, I have given this disclaimer. Oh no, you can't see that, but there you go. I've given this disclaimer to all my other classes, so you're the last one to hear it. But I know my handwriting is atrocious. Okay, if you and it's made worse by the fact that I'm scribbling on a plastic sheet up here, and I have no feedback from it, right? And add to that the fact that this is being projected onto this rough screen and pixelated through that projector. It's very likely that at some point I'll write something up there that you don't know any idea what word that is. And if that's the case, please ask me, because if you're in that boat, then it's most likely that at least several other people are in that boat as well, okay? So I will not get offended if you can't read my handwriting. I have a doctor's handwriting, okay? So there you go. All right, but we have achieved the appearance of multi-programming, okay? It seems like the Jamboard is running at the same time that image in the upper left-hand corner is being processed. It looks like that. Yet we know, okay, so we've got more than one program, quote unquote, simultaneously. Yet we also know that the processor can only do one instruction at a time. Therefore, it can only address the needs of one program at a time. Okay? How do we make these two facts gel together? How do we make both of those things true at the same time? Simple answer, that's one of the main jobs of the operating system. Okay? The OS is in charge of making it look like that's the case. Okay? So I can see some of you in the back craning your necks to read the bottom. I'll try and do better. Do you want me to translate some of this? What does it say? Here? here. It says processor does one instruction at a time. So how do we make these two facts the same? It's the operating system that does that work. That's what we mean when we say the operating system is a resource manager. That's the metaphor that we're talking about. It's perhaps not a very, I don't know, I don't think it's a very good metaphor. Because what do you mean by resource manager? What do you mean by resource manager? Well, it says it right on the tin. It manages resources, okay? But what resource? What resource? Memory is a great suggestion. Memory, absolutely for sure, memory. Okay? Because here's the kicker. You don't have enough memory. No computer has enough memory. If by enough we mean they can keep all the memory, all the needed variables and memory for every application and instructions for every process in main memory at the same time, right? Because there are potentially thousands. And if you're running an operating system like the one that Google runs on their cloud, there could be potentially millions of simultaneously running processes, and there's just not enough RAM, right, on the chips to be able to store all of that at once. Even if you could, you couldn't access it fast enough to meet the standard. Okay? So the operating system is in charge of swapping chunks of memory in and out of active memory as it loads and unloads programs, as programs become active and inactive, okay, or stored. Okay, so that's one of the resources. That's one of the resources that that's the key, really, the key resource that the operating system is in charge of. But others are available too, like access to disks, communication between processes. Okay, we call that inter-process communication. The operating system is in charge of those resources. And anything that needs to be given to, any resource that needs to be allotted to all units of processing, the operating system is in charge of. Okay? Now there's an idea that maybe you probably haven't wrestled with before. How many of you have ever wrote a program that has multiple threads? Okay, nobody. What does that even mean? Have you ever heard hyper-threaded used as a terminology for like, oh, this computer is awesome, it's hyper-threaded, right? A thread is a unit of computation, right? A unit of processing. Just like a process is a unit of computation. You can think of it like this. Every process has at least one thread. Some processes can have multiple threads. Threads should be designed so that they can be run simultaneously. I did quote marks. Simultaneously, okay? Not really simultaneously, but it needs to look like they're being run simultaneously, okay? I'm trying to think, is there a cluster on campus? You know what I mean when I say cluster? It's a machine. I mean, you could argue that the infrastructure lab has one. It's a machine that has multiple processors that can be used as if they are one computer. Okay, and so each processor can simultaneously work on one thread, right? So you make your program so that all the threads can be run at one time, and you can distribute it across some number of processors, and get it finished much more quickly by using multiple processors. Okay? All right, so that's what we mean by resource manager. A operating system is a resource manager. Any questions about that so far? The other common metaphor, and this is also true in your book, that gets thrown around when you talk about operating systems is that it is a quote-unquote bridge. And so what bridges do is they span a gap between two ends, end 1 and end 2. Okay? And so this is why you need, this is your bridge right there. So as a metaphor, we need to know what's on end 1 and what's on end 2. Okay? And when we know that, we can say the gap between those two viewpoints, those two, if you want, abstractions, is what the operating system is in charge of building. Okay? And that's what we mean by the bridge metaphor. So let's talk more specifically about what that means. A bridge between what? Okay. Any ideas?
Priority-based, like which program is better priority.
Okay, so that's one thing that I would put under, and these two metaphors are connected, as we'll see, but that's one thing I would put under what resource, because when you're talking about what process to give priority, you're really talking about how should you schedule those resources. Okay, that's a key word we'll talk about in just a second. So good answer, not quite what I'm looking for. Yeah. Okay. Now, your user's correct. It's not clear to me what you mean by input and output, though. Could you be more specific? Okay. All right. Yeah. Yeah. You've read the chapter. Yeah. Okay. See what happens when you read the chapter before class? You know what's going on. Okay? Sort of. All right. So the two ends are hardware and user interface. Okay. Hardware and user interface. Why are those two things not the same? Well, again, in early computers, they were very close to the same thing, okay? Because when you went to IBM and you bought a computer, it filled a room, okay? It had a printer that came with it. It had memory that came with it, and most of it was on tape reels and could be read in and out, and it had a card reader that came with it, and then the computer itself was a giant box with lights on the front. Or if you back up earlier than that, it's a giant box with plug boards on the front, okay? But the whole thing came, right, as a complete unit, yeah? You can imagine that this is really, this is considered by businesses as a investment in equipment, okay? And the whole thing comes as a single package. There was no concept that I could upgrade this with a modem from another manufacturer. I could upgrade this with a printer from some other manufacturer besides who I bought it from, right? It comes, if it had a monitor, it had a set monitor, a known hardware component, right? It had all the hardware that it's ever going to need for its entire lifetime. This is the idea, is already there, okay? So if you learn to program for that machine, okay, and you want to write a program that uses the printer, you need to learn how to program in the language that the printer understands, okay, using the instructions that that device understands, okay? Each chunk of hardware has its own language. Okay? It needs bits to be formatted in a certain way in order for it to make sense to that chunk of hardware. Okay? As computers got more advanced and the monopoly of computer manufacturers began to break down, and you started to have printer companies, and you started to have modem companies, and you started to have, networking companies, okay? Now you don't buy the entire computer at one time. You buy a base, okay? And it may come with a monitor, but it's not the only monitor you're ever going to have or could possibly ever have. And it may come with a modem, but you can buy another modem, and as long as it's compatible with your machine, you can throw it in there, okay? The user on this side, we can think of at the level of the programmer, okay? How does the programmer, let's say a C++ programmer, for instance, how does the C++ programmer know what hardware is going to be available on the machine where his program is running? What you do as a student is you usually write a program, and one or two people run this program. You run it on your hardware, you send it to your professor runs it on his hardware. We say, great, okay? Probably your professor compiles it for his program, for his hardware, and runs it, right? Now, have you ever tried to send it to somebody, send an executable to somebody else, okay, and have them run it? Maybe it works, okay? But think about this, the more hardware they have, okay, the less likely it is that it's going to work out of the box, okay? Especially if you're having to program, if you program for a specific hardware, right? And they don't have that hardware, they have another company's hardware, okay? So how does the C++ programmer know, once you sell your program, how do you know what hardware is going to be on the customer's computer?
Operating system makes it like hardware independent.
Okay, so the answer to the question is you don't, okay? You need a bridge between these two ends, okay? And setting up that bridge is probably the second major job of the operating system. To make it, as you said, hardware independent. Okay? You've relied on that so far. We all rely on it all the time. It doesn't matter what printer I have, I should be able to print in Word, right? Word is a massively complex, bloated, huge, ugly program, but it doesn't know how to speak HP printer, and it doesn't know how to speak Lexmark printer, and it doesn't know how to speak Canon printer, okay? What it knows how to do is it knows how to ask the operating system to translate what it needs to the specific hardware, okay, that is on that machine, okay? And that's what the job of the operating system is. Now, how that works, at a high level anyway, is what we're going to look at, one of the things we're going to look at as we progress through this semester. Does anyone want to tell me what kind of software the operating system relies on to make that bridge happen? Drivers, yeah. Specifically, you need to have the right driver installed so that the operating system can talk to your hardware, okay? We're going to come back to drivers because that gets important again in just a second. Okay. I want to reiterate that operating systems are not done evolving. Okay? We're not finished evolving operating systems because the driving force that evolves operating systems is changes in technology. Okay? You can trace it from the earliest computer days through to today, through the cutting edge of technology today. Early on, you had vacuum tubes and computers that only ran one program at a time, okay? And so when you programmed for those computers, you punched your program into punch cards. You took your stack of punch cards, or you gave your stack of punch cards. I used to have professors who were old enough to remember using mainframes when they were in early computer science programs at universities in the early 80s, late 70s. And you would punch your set of cards, and you weren't programming at a high level. So you weren't saying like INT NUM1 equals. You were saying 01101, right? Because you'd already translated your assembly language into binary, and so you were punching in the exact binary that you wanted. Okay, and the binary set of instructions and parameters that you needed the computer to have. You'd take it, right, and you would not drop it. Right? Or before you picked it up, you take a big black marker, and you can see these on stacks of computer programs that are on cards now. Take a big black marker and you draw a horizontal line across it, right? Because your stack is maybe 100 cards long. Should you drop it, how are you ever going to get it back together? I'm going to just turn it on in and try and make those lines line up. That'll get you close, right? And then you can go through and double check, okay? All right, so now you don't drop it, and you hand it to the lady at the window, okay, who's running the interface of the mainframe. She takes it and she puts it in the card reader, and then when it's your turn, the machine reads in your program, and however long it takes, you sit there, okay, and it'll then give you a printout, and here you go, okay. This was the program compile test phase, right? If it worked, you're happy. If it didn't work, back to the drawing board, okay? Do that process again, okay? That sounds like a living hell to me, right? But you guys, and me too, you guys are used to being able to hit that compile button at any point, right? That is a marvel, okay? From if you were a programmer 30 years ago, 40 years ago, right? But the operating system, the reason I bring this up is to not say how good we have it. The operating system was different on those machines than it is on the machine in front of you now, okay? Because all that operating system had to do, right? The first operating systems were just memory banks for keeping track of multiple programs. These were called batch processing, okay? That happened as vacuum tubes turned into transistors, as transistors turned into integrated circuits, okay? Now you have extra memory, okay? So that level of operating system needs to start keeping track of what memory is where. As integrated circuits turn into very large-scale integration, VLSI, what we know as processor chips, then you get early forms of Windows and early forms of Mac OS, okay? Now you're starting to see actual multi-programming happening, okay? You're starting to see, as processor chips come out, you start to see the need for creating that bridge between the ugly world of hardware programming and the nice, pretty, comfortable world of the user world, okay? Because why? As operating systems have gotten more complex, the need for computer scientists has grown. Okay? The field has grown. Before operating systems, there were no computer scientists. There wasn't a difference between programming, okay? There wasn't a difference between programming and using the hardware. Now we draw a distinction, and even an academic distinction, between programming, we call them computer scientists, and hardware people, we call them electrical engineers. And there's a distinction between there. Even though there's really no distinction still between software and hardware, right? software is just hardware that can be deleted, and hardware is just fossilized software. Okay? But we draw a theoretical distinction between those two fields. So why are there so many of you in this room? You all expect to get a nice paying job when you're done with your education. What forces have driven that?
The increase in just technology in general.
What do you mean?
How pretty much anything on somebody is a computer, like your
Okay.
phone,
Okay.
iPod.
Okay. Okay. Do your grandparents, your grandmothers have cell phones? Yeah. Do they interface with computers sometimes? Sometimes. They certainly touch them all the time. They use them all the time. Computers have become critical to daily life, right? And they became critical to daily life because they remained easy to use as they got more advanced. Okay? We used to talk in software engineering back in the 90s, and I don't know if it's the same anymore because I haven't really done much official software engineering in a long time. But we used to talk in software engineering about black box design. Have you guys ever heard of that? Black box design? It means that a computer or a system, in this case a computer, is designed where you can use it without having to know how it's designed or how it works. Okay? The average person uses a computer all the time and has no idea how they work. Right? Can you imagine how crazy that is? Yeah? How crazy that would be to someone in 1960 who like, hey, why do we care about computers? Because there's going to be one in every house, and because everyone's grandmother is going to get on this thing called the internet, and she's going to talk on this thing called Facebook. You sound insane to a person in 1960, 1970, 1980. Okay? But that is exactly what's happened. And those are the forces that have been allowed to happen because the middleman between the easy-to-use interface, I always push this button if I want this to happen, and the complex, the infinitely more complex back end of how that happens, right? That bridge has always been, that gap has always been bridged, right? And it's been bridged with the operating system. Are we done? Are we done expanding that gap and having to make better operating systems to bridge it? No. Can you think of an example of how this is happening? Where's this file? Because I can scribble on my iPad, and if I'm not in the way, you can see it. There you go. I can scribble on my iPad, and it shows up on this screen. Where is this file? It's in the cloud. What is that? You can think of the cloud as somebody else's computer. Okay? But the truth of the matter about the cloud is it's not one computer, it's millions of computers. Okay? And we're just using a particular application that runs as if it's running somewhere else. Okay, but I have access to it at two places simultaneously. Okay, so from the user perspective, I don't even have to think about that. But behind the scenes, the operating system that is running this program is way more complicated than even the operating system on the machine in front of you guys. Okay, because it's got to bridge a much more complicated hardware gap. Okay, and this is nothing. This is low-level cloud. This is software as a service on the cloud, right? What about infrastructure as a service? Okay, there are companies who don't have computers. They rely entirely on having their entire computer technology, internet, everything provided to them by services on the cloud. Okay? They get to feel like they are using their computer, but they're not. Okay? So the operating systems that run those things, the operating systems like Amazon Web Services and Google Cloud that allow those to be built, those services to be built have to be super complicated. Okay? And the abstraction keeps getting expanded and expanded and expanded and expanded. Okay? I would note, though, that I wonder if there is a limit to the benefit of hiding the details, okay? Because you might argue that in some ways that this is kind of a concerning trend, because computer users more and more know less and less about the computer systems they're using and are more and more dependent on the middleman to tell them not only how to use their computers, but what they can even do with those computers. Okay? This is why I'm glad you're here in a 400 level computer science course. And I wish there were more people taking 400 level computer science courses, because power and control over computer systems means liberty in the future. That's it. There's no other way. If you don't have control over your systems, somebody else is driving for you. Okay? That's as close as I'm going to get to an ethical discussion in this class, though, I think. Right? But I think it's important. I think it's something that we all have to wrestle with as professionals. Okay. So today, there are in an OS system, an OS software components that contain all the functions, right? Operating systems have millions of lines of code. Okay? They have millions of lines of code in order to provide all the services that they need. So let's talk about a little bit how operating systems, out of 30,000 foot view, how operating systems are organized. Okay? It's, of course, way more complicated than I'm going to get into today. And it's actually way more complicated than we're going to get into this semester, because this is just introduction to operating systems, right? That's all we can do in one semester. But I want to start by introducing the two main components, the two main worlds, if you will, of modern day operating systems. And they are kernel, Kernel, and user space. Okay? These are such powerful distinctions that not only does the operating system enforce these distinctions, but they're also enforced at the processor, at the CPU level. Okay? So let's talk about what this is. What's a kernel? If you don't know the answer to that, what does the word kernel mean to you? Outside of this room, outside of operating systems, where do you hear the word kernel? Kernel.
In Android phone, we have kernel for manage the resource and
Sure.
something.
Sure. That's the operating system kernel for Android. Yeah? Linux has kernels. Android has a kernel. The Linux kernel determines what version of Linux you are running, right? It's maintained by one guy. Somebody help me. Linus Torvalds. Okay. And Windows has a kernel. Okay? They probably don't call it kernel because they like to rename everything, but they have a secure space. And that's what a kernel is. It's the fundamental parts of the operating system. Okay? I'll give you a better definition in just a second. The word kernel means like seed. Okay? It's the thing at the root of the system. Okay? You had your hand up because you wanted to tell me what a kernel was. And I already know you read the book. So tell me what a kernel is. Okay. I don't want to talk about privileged instructions yet, but you're absolutely right? I want to talk about privileged instructions in just a second. Let's give a different definition. The kernel is the operating system software component that contains all functions for managing the system. That includes the most essential services like services for memory, device management, creating and managing processes and threads, or any other kind of unit of computation, communication between concurrent system activities. Okay? So any system that is fundamental to one of the two fundamental jobs of the operating system, any software component that reveals that functionality can be bundled as part of the kernel. Okay? It's like it's what makes your operating system your operating system. Okay? One of the reasons why we have this is for security purposes. Okay? And I don't mean necessarily like forensics. I don't mean it at that level, although it could have to do with that. I don't mean computer security at the digital forensics level. I mean, we want to keep processes from screwing things up, whether they're doing it maliciously or they're doing it out of ignorance. Okay, accidental or malicious. Okay, what's the old saying? Never ascribe to maliciousness anything that could just as easily be ascribed to incompetence. Okay, right? So it could be that somebody wrote an incompetent piece of software. It could be that they wrote a bug. They wrote a virus even. Okay. Either way, what that program is doing is breaking the rules of the system. Okay. So what the kernel does is it puts all of the software, all of the calls to the operating system that can break the OS rules inside of a sandbox called the kernel. Okay, groups them all together, right? And so you have to have special privilege to have access to that functionality. Okay, this is where. Tell me your name. Austin? Is that right, Austin? Okay, this is what Austin was talking about with privileged instructions. Right? Privileged instructions. Those are CPU instructions that perform critical operations that access I/O devices and the CPU's status and control registers. So any CPU instructions, or can you not see? Yeah, that would help if I did hit this button, wouldn't it? Okay, thank you. Any CPU instructions, okay, that deal with device management, and that deal with CPU registers or any other kind of program state. Okay? Those instructions are privileged instructions. Okay? So in other words, not everybody, and by everybody I mean not all programs that are running on the machine, right, get to change CPU registers. I may have asked this before, but any of you taken architecture yet, or done anything with computer architecture, cache memory, and that kind of stuff? So every processor is made up of, and we showed this picture before, right? Every processor is made up of the arithmetic logic unit and then certain certain caches that mean certain things. So like literally inside the processor, you've got memory for the set of instructions for the program you're currently running. You've got a pointer to the instruction that needs executing next. And then you load that instruction into the CPU, into the ALU. It chugs. And if it replaces something in memory, it puts it back in memory. Imagine what would happen if anybody, so there's a piece of memory on the processor that remembers what needed to happen next, okay? Imagine what would happen if any program could just say, yeah, whatever you were doing before, skip that, go to this location in memory and run this program. That's what a virus is, okay? That is what a virus is. It injects itself into a running program and makes the machine, tricks the machine into running some other program. So to limit viruses and also to limit just bad programming, we have a set of CPU instructions that can only be executed if the program is in kernel space, not if it's in user space, okay? So this is what we mean by kernel space and user space. Here we can execute privileged and non-privileged instructions. Here we can only execute non-privileged instructions. So most of your programs, most of the programs that you write, most of the programs that you run, spend all but a little bit of their lives in executing in user space. And they have their own memory that doesn't bother anybody else. If they screw up and do something wrong in their own memory, okay, and the program crashes, too bad, so sad, the program crashed, but the computer is fine, and the other programs that are running, that are being managed by the operating system are fine, okay? Over here, that's not the case, right? So we only allow occasionally to go into kernel mode, okay, for very specific reasons, right? One very common reason why we have to go into kernel mode is, we talked about this before, I think it was right here. Drivers. Because notice, privileged instructions are those that deal with device management as well, okay? And that's what drivers do. They deal in device management, right? They deal at the low-level bits, okay? And so they are constantly having to go into kernel mode. They're constantly allowed into kernel mode to execute those sensitive instructions. So that is why when hackers and people who make viruses and other malware start to target software looking for the hallmarks that they need, the mistakes, that's what they are, they're mistakes. Buffer overflows is the main one, right? Not having a correctly bounded buffer, which C++ allows and has been the bane of all programmers and all system administrators since the 80s, okay? And it's gotten a little bit better, but this isn't a computer security class. If you want to hear my speech about this, take my computer security class later, right? But device management happens in kernel mode. So if you find a driver that has a buffer overflow in it, you write a virus that makes use of that buffer overflow, it's very likely that device, that software, that driver, will be in kernel mode. And then you've pwned the whole computer, okay? So it's not a perfect system. Everybody knows how it works, and so you've got to have good drivers, right? But this is one of the things that the operating system does. It maintains these two different spaces: kernel space, where privileged instructions can run, and user space. All right, any questions about that? All right, so I want to talk about the concept of what it means to interact with an operating system. Okay? Interacting with an operating system. Have you used an operating system today? How many? 2? One on your phone, one here in front of you? Yeah? Okay. What did it mean to interact with your phone? What did that look like, to interact with the operating system on your phone? So you picked it up, and if you don't have your mask on, it might recognize your face, but otherwise you type in your PIN, okay? And then you've got a desktop, okay? What effectively is a desktop? It has icons on it. It's got other things that you can set up. There are icons or buttons for you to push. Each button loads a new application. Each application provides services to you, okay? That's one way to interact with an operating system. On this operating system, this is what interacting with the operating system looks like, okay? Those are both examples. Those are both examples of graphical user interfaces. Okay? Isn't there a what's the lab down the hall called officially? The Human Computer Interface Lab, right? One of the things they talk about in that IT class is what's the best way to create an interface that's usable, that's user friendly. Okay? And that's what we've tried to do over the last 20 or 30 years with this system, is we try to make it user friendly to the outside world. It's a layer of abstraction, okay? Because when you click on this, you are actually running this program, okay? You're running stuff in that directory, okay? You could run that directory without having to click on anything, okay? It's just a shortcut to a program itself. Try teaching your average person that, though. Like the biggest, so my dad always calls me whenever he has a problem with his computer, and it's always like, hey son, Google got deleted from my computer. I'm like, okay. So I have to take a minute and gather my thoughts, because he believes Google got deleted from his computer. You and I both know that's a functional impossibility, because it was never on his computer, right? What happened was something changed to move the button away from where he expected it to be. So therefore, Google is gone, okay? That kind of thing shows the power of this layer of abstraction. Okay? You're so used to it, you tend to think about Windows as being the graphical user interface for Windows. When you log into a machine and you look at the graphical user interface, you're saying, this is Windows 10, this is Windows 7, this is Windows 95. You're saying, okay, well, this is obviously a Linux distro, Unix or whatever. Oh, this is a Mac, okay, because it looks like a Mac. Right? The graphical user interface looks like a Mac. And quacks like a Mac and walks like, no, whatever. Right? It acts like a Macintosh, okay? But I want to strip away the the graphical user interface. And I want to look down below that and get closer to the metal, okay? One layer closer to what an operating system actually is, and therefore what a computer actually is. And that's where we're going to be dealing with command line. Whew, sorry. Command line. How many of you have ever opened up the terminal? Do it? All the time? So on Windows, it's called command prompt. It's a similar idea, right? Here it is. This is a command prompt. What am I looking at? I'm looking at my files. You're going to see me struggle to use the right language here because I don't use Windows. But I'm looking at the files that are available on my account. So if I want to go to my desktop, I'll change directory to the desktop. And then I'll look and see what's on the desktop. Oh, those are the files on the desktop. And if I know the name of a program that opens those files, I can type the name of that program, and I may even have to give the full path to that program, right? And then space the name of that file, and it'll open up, okay? It'll run without having to use the graphical user interface. Windows is not a great environment for doing this in. What is a good environment for doing this in are any of your Linux or Unix-like systems. Okay, one such Unix-like system that is available to you is the server that's at cs.csis.work, and that's the computer science server. You'll see that I have listed a link to a YouTube video that I created for you, okay? That walks you through how to access that server. And if you also all should have received a cryptic message from me on Canvas that had your username, which is the first 2 letters of your first name and the first 4 letters of your last name, followed by a pipe symbol, which you can ignore, followed by your password, okay? And this shows you how to log in and use the shell. Likewise, I have some user notes here that you can have access to. I called it yet another Linux tutorial, okay? That textually walks through what I talk about in this video, and then I have what I found to be a helpful web page about the basics of using, quote unquote, the shell. Okay, great. So we introduced a new topic. What is the quote-unquote shell? Okay, so I talk about this in some detail on that video in more practical terms, right? But what the shell is it is a program that waits for commands from the user and passes those commands to the operating system to be processed. It's like, you can think of it as the front door of the operating system, okay? And just because the shell is running on your computer doesn't mean that you're accessing anything onto your computer. If you have logged in, you are using the shell via the terminal on your machine to access the file system and your files and any programs that are on the remote machine, okay? And so one of the things we're going to do is to get our hands a little bit dirty with actually working with operating systems at the programming level, is we're going to eventually write our own simple shell for that server, okay? But before we do that, I wanted to give you the opportunity, for those of you who've never done anything like this, to get your hands dirty just living on another machine, using another computer without having a graphical user interface. Okay, and that's what that first assignment, which is due Monday, is that right? August 30th? Sunday night before midnight. Okay? That's what that's all about. All right, let me see if I want to tell you anything else. Right, the graphical user interface is intuitive. The reason why you want to use the shell is because it's quicker as long as you know how to use it. Okay? It's more lightweight. It doesn't cost as much processing as the graphical user interface does. And also, your your reading introduced the notion of a shell script, right? I could have replaced you with a small shell script. Is a real burn, right? But you have to know what a shell script is to understand why that's the case. Okay, and that's one of the things that I haven't said specifically about, but it's a powerful thing that you can look up and that you'll need to look at when you read the chapter. Okay, I think that's it for today. Have you guys got any questions? If you have not read the chapter yet, you are supposed to. Okay, we're going to be moving on to chapter 2 next week. In fact, what chapter 2 covers is the fundamentals of processes. Okay, so we're going to start getting into the nitty gritty about how an operating system works as a resource manager. Okay. All right. So if there are any questions, then I will see you next week.
Excuse me, sir.
Yes.
How about a lecture on Monday?
Yeah, so we covered the same material, but I will post them both. I'm just waiting, and I just wanted to wait till after this lecture to post them both at the same time. So either later today or tomorrow, I'll post them both.